We talked about linear independence of vectors in general last time. Now I want to look at the special case of linear independence of column vectors in Rn. So let's let v1 through vk be vectors in any space. Recall that the set v1 through vk is linearly independent if the only linear combination c1 v1 plus dot 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 plus ck vk that equals 0 is 0 v1 plus 0 v2 plus up to 0 vk. The set is linearly dependent otherwise. All right, now let's look at the special case that those k vectors are in Rn. So let's suppose v1 through vk are column vectors in Rn. And let's define the matrix A to be the matrix that has v1 in its first column, v2 in its second column, etc. Then the set v1 through vk is linearly independent if and only if the only solution to A c bar equals 0 is c bar equals 0. Now there's a couple special cases that are worth pointing out. K could be greater than n, it could be equal to n, or it could be less than n. Actually, let's do the special case k greater than n first. If k is greater than n, that means that the matrix A looks like something like that. It's much wider than it is tall. Then we can imagine what happens when we do row operations to find a matrix in row echelon form. We're going to have a 1 and a 1 and a 1 someplace, but certainly not a 1 in every column, because we've only got n rows and we've got more than that many columns. So row echelon form will not have a 1 in every column. So that means there will be free variables. And whenever there's free variables, there's infinitely many solutions. And if there's infinitely many solutions, then C equals 0 is not the only solution. So to sum this up, we can say more than n vectors in, well, in Rn, let's say, a collection of more than n vectors is linearly dependent. So you don't even really need to do any calculations. If you see that there's more vectors than the dimension of the space we're in, then it has to be a linearly dependent set. Now let's look at the special case that k equals n. So then A is an n by n matrix. Then AC equals 0 has a unique solution if A is invertible. That unique solution is going to be C equals A inverse 0, which is just the 0 vector, if A is invertible. It has infinitely many solutions otherwise. Because if it's not invertible, then when we do row reduction, we're going to get a row of all zeros at the bottom, at least one. And then that means there's going to be some columns that don't have ones in them, and therefore some free variables. So the summary of this analysis is that n, or in Rn, a collection of n vectors is linearly independent if and only if this determinant that uses those n vectors as column vectors is not 0. Right, now let's look at the special case that k is less than n. Then A is sort of a tall and skinny matrix. The columns are linearly independent if the rank of A is exactly k. So we'll have to use row operations to see this. That's usually not something we're going to be able to see just by looking at it. So let's do an example of that one, since that's the only one where we need to do some computations to decide what's going on. So for example, let's ask if 1, 2, 1, 3, 0, 1, 2, 2, and 1, negative 1, 1, negative 1 form a linearly independent set. So are these three vectors a linearly independent set? So we'll do row operations. We've got 1, 2, 1, 3, 0, 1, 2, 2, 1, negative 1, 1, negative 1. We can use this 1 to make zeros below it, so we'll let row 2 be row 2 minus 2 times row 1. Row 3 is going to be row 3 minus row 1, because it's got a 1 in it, and then row 4 can be row 4 minus 3 times row 1. And then we get 1, 0, 1. 2 minus 2 is 0. 1 minus 0 is 1. Negative 1 minus 2 is negative 3. 1 minus 1 is 0. 2 minus 0 is 2. 1 minus 1 is 0. 3 minus 3 ones is 0. 2 minus 3 zeros is 2. Negative 1 minus 3 ones is negative 4. And then we can use this 1 in the second row to get rid of the 2's below it. So row 3 becomes row 3 minus 2 times row 2. Row 4 becomes row 4 minus 2 times row 2. And then we have 1, 0, 1, 0, 1, negative 3. You know what, that's silly. We could divide this one by 2, and then, oh no, maybe what I'm doing is better. I could have switched those two rows, but of course there's many ways to do these things. So I'll keep going with what I'm doing. So 3 becomes 3 minus 2 times 2. 2 minus 2 ones is 0. 0 minus 2 negative 3's is positive 6. And then 4 becomes 4 minus 2 times 2. So we've got 0. 2 minus 2 is 0. Negative 4 minus 2 negative 3's is negative 4 plus 6, which is 2. And then, well, we can see that the rank is 3, because if we do one more step and we let 4 become 4 minus 1/3 of 3, then we'll get rid of the 2 there, and we'll see that we have rank exactly 3. So rank equals 3, and that means that the vectors are linearly independent. The end.